Hello, this is an introduction to a simple app that I've written using the help of Claude AI to introduce kinematics as applied to projectiles. Projectiles are objects which are thrown through the air, moving both horizontally and vertically at the same time. The object moves with a parabolic path or trajectory. For projectile motion, you apply the SUVAT techniques from one-dimensional kinematics. The application of SUVAT takes a little bit more effort and a little bit more time in the projectile case. You have to be very careful about separating out the vertical and horizontal motion. The homepage of the app appears very similar to other apps that I've written using Claude AI, with an introductory page. And then at the bottom of the page are some buttons that when you click them will link to more information about the topic being presented and discussed within the app. Let's just click the first button, reading the question. First of all, we have to ask ourselves, how do we know the question is about projectiles? And that'll be the very first step in solving the problem. We look for keywords. Projectiles is an obvious one, but there might also be a question about range, or the maximum height, or the time of flight, or the angle of projection. Remember, the object is moving through the air under the influence of gravity, and it's moving horizontally and vertically at the same time. We have to have some information, or maybe we're asked to work out its initial motion. So we need to know how fast it's moving and what angle that motion is in relation to the horizontal ground. A key idea in any kinematics question is about directed motion. The motion, we have to understand the direction. Is the object going up or down, or left or right, or north or south, or is it perhaps doing two or even possibly three of those things at the same time? Movement where we have a distance travelled is essentially the displacement with the direction included in that motion. When we talk about speed for kinematics, we're interested in velocity, which is essentially the speed plus the direction of that speed at any moment in time. And finally, we have acceleration, for which there's no separate word to convey the idea that the acceleration has a direction, but it most definitely does, and it's essential in capturing that correctly so that you can work out the problem. Some other fundamental ideas involved in a projectile question is the idea of independence of motion, in that the object travelling from left to right or right to left, in my view, and left to right in your view, is independent. That horizontal motion is completely independent of the motion as the object moves up and moves down. They're happening simultaneously, but we perform the calculations essentially independent of each other, and at a later stage we may bring the equations together. What's also important is that the horizontal motion has a constant velocity, and the vertical motion has an acceleration always down towards the centre of the Earth due to gravity. We extend the notation that we used for SUVAT questions by including a subscript that indicates which direction we're interested in. So for displacement S, we can talk about horizontal displacement Sx and vertical displacement Sy. We can also talk about initial and final velocities Ux, Uy, Vx and Vy, and similarly accelerations in the horizontal and vertical direction, although in this case there is no horizontal acceleration. Diagrams are as important, if not even more important, with projectile motion as they are in one-dimensional kinematics. We have to establish a coordinate system which involves identifying an origin or a place from which we are measuring the motion, such as its displacement. We have to know where the object starts, that will be our origin, and we have to split the velocity into two components, usually horizontal and vertical. Now if we look at how we build those axes and how they relate to the motion, we take a point from where the object is moving. Let's mark that with a black dot. And then we put a horizontal axis along the ground, and we'll label that X. And then again from the dot, we'll put in a vertical axis, which we'll label Y. And now finally, we'll have a little animation of the object as it moves from the origin through the air to the other side, which in this animation is from left to right. So that's creating and defining the axes. Then we have to assign values to the properties of the motion. So for this animation, we've still got the same X and Y axes and the origin, but the animation shows that as the object moves from left to right, it has a horizontal velocity, Vx, and a vertical velocity. And if you watch the animation, you should be able to see that the horizontal velocity, Vx, never changes, and the vertical velocity is changing as the object goes up and then goes down. At any moment, we can take the object and we can say that it has a horizontal displacement from the origin, Sx. And at the same moment, it has a vertical displacement, Sy. And at the same moment, it has a horizontal velocity, Vx. And it has a vertical velocity, Vy. It also has an acceleration, but that's always downwards, and that's constant. The kinematic equations that we use are the same Suvat equations that we use for one-dimensional motion, but we recognise that the horizontal motion has a constant velocity, so we have much simpler equations we can use. Vertically, we're going to use the Suvat equations, such as S equals ut plus a half at squared, and in these examples we're adding the initial displacement if the object is actually starting higher than the point from which we're measuring, and this is denoted by y0. There's a solution method page, but essentially it's the same as the 1D kinematics, by separating out the equations for horizontal motion from the equations for vertical motion. And briefly, there are pages with standard results applying the kinematic equations, the Suvat equations, to an object as it's moving. The first set will identify what the velocity components are, horizontally Vx and vertically Vy. Now for all of these examples, when you click on Learn More, it will reveal the working that the application used to create these equations. So here we have an example for the horizontal and vertical velocities. Here we have an example for the range, where v0 is the initial velocity and theta is the angle that the object was launched from the vertical. Here we've got an equation that will show the time of flight, how long it takes for the object to move from where it starts to where it finishes, where v0 is its initial velocity at an angle theta to the horizontal, and g is the acceleration due to gravity. The final example on this page is where we show the coordinates, the x and y values of the position of the object at any time, where we are inputting its x values, how far it's travelled horizontally, and calculating what its y coordinate will be at that particular moment. This is more complicated because we have to merge together the equations of the horizontal motion from the vertical motion, and all the detail is provided down here. The last page is similar in that we've got some worked examples, but they include numbers. So if we have an object thrown from the height, maybe it's from the top of a tower or from a cliff, and we have to find out where it lands and what its velocity is on impact. So the solution step by step is given here. For all the standard results and for all the worked examples, as in any practice or learning the topic, attempt the question on your own first and then check your answer against the step-by-step solution until you're able to answer the question on your own without looking at the answer. The link to the app is given below this video, and I hope you find it useful and informative. Goodbye and keep on studying.